on revision worksheet 7. So there's two questions on this revision worksheet. The first one is from 2017 paper 2 section A, question 2, and the second one is the 2017 paper 2 section B, question 8, but only the second part of that question, so just part B. So these are both focusing on statistics questions coming from paper 2. So the first question, an experiment measures the fuel consumption at various speeds for a particular model of car. The data collected are shown in the table 1 below. So the first thing they ask us to do is find the correlation coefficient of the data in table 1. So that is minus 0.957. So I'm going to run through very quickly how to calculate the correlation coefficient, first on a Sharp calculator, then on a Casio calculator. If you know how to do this, feel free to skip on to the next part of the question. Otherwise, I'm going to go through, like I said, Sharp first and then Casio. So to calculate the correlation coefficient on a Sharp calculator, the first step is always to clear our memory to make sure that there's nothing saved there from a previous question. So to do that, we press the second function, the orange button, followed by alpha, because above the alpha in orange it says M-CLR, which stands for memory clear. When you click that, you should get three options. 0 is for display, 1 is for memory, and 2 is for reset. So we click number 1, memory. And then it'll ask you all memories, 0 to clear. So click 0. And it should give you a message saying all memories clear. So that's cleared, so we're definitely starting with a blank slate. The next thing we want to do is to switch it to statistics mode. So what we do is we click mode, which is on the top right hand corner, and you should get three options: normal, statistics, and drill. So we want to click into statistics, which is number 1. When we're in the statistics menu, they should give you 5 and more options as you scroll down. But what we're looking for is line 1. So line, it stands for linear regression. So click into 1. And now at the top of the calculator, it should say stat 1 and in square brackets line. So that's what we want to do to enter our correlation coefficient. So now that we're in the statistical mode, we're going to start entering our data as points. So the first point is 40, 21. So think of it like an X and a Y. So we type in 40 and then we need the comma. So the comma is on the second row on the very right hand side, and it has a comma on top, and then underneath it, it has bracket X comma Y close bracket. So if you click that, it should just come up as a comma for you, and then you put in 21. In order to save that point, we use what's called the data button. It says data above the button. The button itself actually says change, and it's got the arrows circling around it. It's at the very bottom row on the right hand side. So when you press that data or change button, you should then get a data at the end of that point, and at the bottom of the screen it should come up data set equals 1, which is saying that you've entered 1 point into the data set. So you continue doing that for all the points. So we'll do 48, 16 data, so that should say data set 2, 56, 18 data, that's data point 3, 64, 16 data, and that's data set 4, 88, 13 data, and that's data set 5, 96, 11 data, data set 6, 112, 9. Data, and that's data set 7. So just double check, yes, we've only 7 points there. So once you're happy you've the 7 points in and correct, we're then looking to calculate the correlation coefficient. So to calculate the correlation coefficient, we're looking for its symbol, which is OR. So on the Sharp calculator, the OR appears in green just above the divide button. So in order to use that, we press alpha and the divide button, which we get OR, and then equals. And what you'll find is it gives us OR equals minus 0.956573405. So they want that correct to 3 decimal places. So for 3 decimal places, we're going to cut it here. Since the next number after that is 5, we're going to round up, which is minus 0.957, which is where we got our answer. So if you're using a Casio, the way that we work to get the correlation coefficient on a Casio, we first start off by clearing its memory. The way to clear the memory on a Casio calculator is pressing Shift and the number 9, which is CL or above it. When it gives you the menu, 1 is setup, 2 is memory, 3 is all. So let's clear its memory, number 2. And it'll ask clear memory equals for yes, AC for cancel. So we'll press equals to clear it. You should get a message now that says complete and press the AC key. So we'll press the AC key and now we can get this into statistics mode. So to do that, we click the mode button, which is on the top right hand side, and underneath once we click the mode, we'll get 4 options and we want to go for 2 statistics. And when we're in the statistical mode, we want to look for its linear function, which is a plus bx. It's number 2. So we'll click number 2. And what we should get now is a table that has 1, 2, 3 on the left, and then 2 more columns, and one column is called X and the next is called Y. So this is for entering our data points. So in our table, this here is our X and this here is our Y. So we're going to enter like that. The easiest way to enter these points is to enter all of the X values, then all the Y values. Just make sure that they're matching up. So first we type in 40. To put it in the tables, we press equals, and then we'll continue down the X. So we'll do 48 next, then 56 equals 64 equals 88 equals 96 equals 112 equals. And you're down on to row 7. So if you click using your replay button, the circular button at the top, you can use the arrows to go right back up to number 1 and then to move across to the right to the Y's. Then we're going to start entering the Y's. The first one is 21, again press equals, 16 equals, 18 equals, 16 equals, 13 equals, 11 equals, and 9 equals. At this point, just double check that both of your X and your Y's end up at the same place. So they should both end up on the 7th line, so beside the number 7. And when you're happy all that data is correct, we press the AC button. So then we want to bring up our statistics menu, and we do that by pressing Shift and 1. And when we're in the statistics menu, we're looking for number 5, which says REG beside it, which stands for regression. And when you go into that, you should see number 3 is your OR. So we press 3. And on your screen now, you should have OR. To figure out what OR is, you just simply press equals, and it will bring up the same number. Now, my Casio actually gives an extra digit at the end, so I have a 3 here. But the same idea, we want to round to 3 decimal places. So we show underneath that if we cut it after 3, the next number is 5, which rounds it up to minus 0.957. My advice for questions like this is, you know, it's very easy to get it wrong, and I suppose just be very careful entering the data. This is one that you'll show right or wrong. But a good habit to get into when we're doing any kind of rounding is not to do it in your head, to write down the full number and then to show your rounding. Because if, for example, you just accidentally do something wrong, you see something, you miswrite something, and it's very easy to see if you've written down the full version and then show your rounding. So it's a good habit to get into. So part B then, plot the points from the table on the grid below and draw the line of best fit by eye. So let's start plotting our points. Now, just to warn you in advance, this screen doesn't particularly like plotting points, so I'm going to have to draw them quite big, because otherwise they'll disappear. So the first one is 4021, which is roughly there. Obviously, if you're using a pencil, you can be a lot more accurate than I can on this. So 16 is here. 56, 18. The next one is 64, 16. So 64, 16. The next one is 88, 13. The next one is 96, 11. And the next one is 112 and 9. Okay, So there's our points drawn, and the second part is to draw the line of best fit. Make sure you're always using a ruler at this. Just bear with me because I'm going to try use the ruler on the screen, but it's not the easiest thing to do and it can upset the whole thing. So I'm going to try draw it in as best I can. I really will try, but just bear in mind that I'm trying to use a ruler on a screen. So roughly speaking, we'd expect the line to be somewhere. Oh, mine has gone a little bit off. So I apologize, that's me trying to use the ruler on the screen. So let me try one more time. Okay. Let me try clean this up. Okay, so this is a little bit better. So what I'd envisage is that it would actually go through these kind of 2 points here. So if you notice, it's going through this point here and this point here. And that's roughly the line of best fit. So the slope of the line of best fit is found to be minus 0.15. What does this represent in the context of the data? So I'll just put it in here to save me having to write it, as my writing can get very messy again with the screen. So there's two ways I suppose you can think of it. So it says as the speed increases by 1 kilometer per hour, the average distance travelled on 1 litre of fuel decreases, because it's negative, by 0.15 kilometers. The other way you can look at it is the rate of which fuel consumption in kilometers per litre is decreasing as the speed in kilometers per hour increases. So either of those is the way to look at it. What's to be very, very careful of here is that you're not directly comparing correlation to the slope. The only thing that the correlation and the slope have in common is the sign. However, remember that the slope is just another way to basically measure the tan of the angle. And we know that the tan of the angle can go up to any number. So just be careful there. It doesn't have to be between 0 and 1. So it can go beyond +1 and beyond -1. The correlation coefficient, however, is limited to be a value between +1 and -1. So the slope does not mean the correlation coefficient. And that's really what they're trying to get to here. Do you understand that that's the case? And do you understand what does the slope represent? So the slope is just basically related to the actual graph itself, which is comparing speed and how much fuel that it's using. So the next part then, Mary drove from Cork to Dublin at an average speed of 96 kilometers per hour. Jane drove the same journey at an average speed of 112 kilometers per hour. Each travelled 260 kilometers and paid 132.9 cents per litre for their fuel. Both used the model of car used to generate table 1. Find how much longer it took Mary to complete the journey and give your answer correct to the nearest minute. Okay. So they're asking us about time. So if you can remember back to your DST triangle. So I'll put it in here. Okay, so they want time. So taking that, time is equal to distance over speed. So that's what we're working with. So Mary, let's look at, excuse me, let's look at Mary first. So Mary travelled a distance of 260 kilometers at a speed of 96 kilometers per hour. So that's how long it took her. Excuse me. And then we have Jane. So Jane then, apologies, this won't change the colour now. My pen has got a mind of its own at the moment, so just bear with me. So Jane, she also travelled 260 kilometers, but she did it at a speed of 112. So we can work that out. We can work out each of them. And they've asked to complete the nearest minute. So when we do that, we basically want to say 260 over 96 minus what Jane did, which was 260 over 112, because that's the difference, or how much longer it took Mary. So what that works out as for us is 0.3869. However, because we were given kilometers per hour, that answer is in hours. So this is in hours, but they asked us correct the nearest minute. So then if we want to convert that, so we want to multiply by 60 then to get to minutes. And what we get is about 23.21 minutes. And correct the nearest minute is just going to be 23 minutes. 23 minutes. So quite a straightforward question there. Just about distance, speed, time. So part 2 then, based on the data in table 1 and their average speed, find out how much more Jane spent on fuel during the course of this journey. Okay, so what we know is that the cost per litre of fuel is 132.9 cents. But if we want to work in euro, that works out at 1,329 euro per litre. So we also know that Mary, if we go back to the question, I've taken it off here now, but we knew that Mary was travelling at a speed of 96 kilometres per hour. So we know that for 96 kilometres per hour, the fuel consumption, so that was kilometres per litre, was 11. So that came directly from our table. So if you go back to the table at the start of the question, you'll see that. Then we had Jane, who was travelling 112 kilometres per hour. And what we know about 112 from our table is that it was 9 kilometres per litre. So in order to work out how much each of them used, we need to take how far they travelled, which for each of them was the same. It was 260 kilometres. And we need to figure out, well, how much they paid. So we know for Mary, she travelled 260 kilometres. She got 11 kilometres per litre, and each of those litres cost her 1.329. So that was for Mary. Then we had Jane, and we knew that Jane also travelled 260 kilometres, but her fuel consumption was 9 kilometres per litre, and again she paid the same price. So what we work out as for Mary, she ended up paying 31.41 when we rounded to 2 decimal places, and the reason we're rounding to 2 decimal places is because it's money. And Jane then, she worked out paying 38.39 for her journey. So the difference between 38.39 and 31.41 works out to be 6.98. So Jane spent 6.98 more. So we're just taking those two numbers away. So question 2 then. In 2015, in a particular country, the weight of 15-year-olds are normally distributed with a mean of 63.5 and standard deviation of 10. So because we're dealing with all, so let's go through, because we're dealing with all 15-year-olds, this mean is given by mu, and the standard deviation is given by sigma. So in 2015, Mariska was a 15-year-old in that country and her weight was 50 kg. Find the percentage of 15-year-olds in that country who weighed more than Mariska. So we're trying to figure out what's the probability that the weight is greater than 50 kg. That's effectively what we're trying to figure out. So let's write that down. We want to find the probability that the weight, and we'll call that x, is greater than 50. Okay, so we don't want the same as her, we only want bigger than her. What this will give us is the percentage of those who weigh more than 50. So remember, the probability is the same as a proportion. However, we can't really deal with x is greater than 50. We have to normalize it. So to normalize it, we use our normalization, well, the normalizing formula, which is in your log tables, and it's given as z is equal to x minus mu all over standard deviation. So we sub into our formula. X in this case is 50. We're subtracting our mean of 63.5, and that's all over 10. So what we're actually looking for in terms of z is the probability that z is greater than minus 1.35. However, if we were to look at the table for normal distribution and look at our z-scores, the z-scores go up as positive. There's no negative, so we need to be able to change this from negative to positive. And how we do that, it's the probability that z is less than 1.35. Now, if you want to revise the probability, especially this section, and how to move with a negative, how to move from greater than to less than, and all that, I would advise you just to check out the probability video. It's in the same channel here, and it goes through this in a lot more detail. For now, I'm just going to say the probability of z greater than minus 1.35 is the same as probability z is less than 1.35. So at this point then, I can look it straight up in my tables, and when I look up 1.35 in my tables, I get 0.9115. And if I want to turn that then as a percentage, which the question asked me for, it's 91.15%. So part 2 of that question, in 2015, Kamal was a 15-year-old in that country. 1.5% of the 15-year-olds in the country were heavier than Kamal. Find Kamal's weight. So heavier, we're talking greater than. So basically what we have here is we can structure it in the form, the probability that some number is greater than A. So we don't know what that weight is. A is the representative, the standardized representation of Kamal's weight. But we know that that's equal to 1.5%, but we don't deal in percentages for this table. We say where Z is greater than this A is equal to 0.015. Now, when we go to our tables for our z-scores, we can't use greater than. We have to work with less than. So what we end up with is we have, well, the probability that z is less than a is basically 1 minus 0.015. So the probability that z is less than this number a is 0.985. So if you go to your tables and look up that value to figure out what the z-score actually is, we end up with a is equal to Now that doesn't represent Kamal's weight, that represents the standardized version of his weight. So we have the formula, the standardization formula that we used in the previous part, x minus mu all over sigma, and that's equal to 2.17 in this case. 2.17. So if we fill in what we know, well, we don't know x, that represents actual weight, minus 63.5, which is our mean, and our standard deviation is 10, is equal to 2.17. And we basically work out then that x is equal to 85.2 kg. Now, I've used the letter A, and that first Z is a capital Z. And that's just working with our standard normal tables. However, you can use a little z, but that I think led to a lot of confusion last year. You can use a different letter. I would just say be careful with the letters. I've just taken A because A doesn't come into it anywhere else. So basically for these ones you have to work out, well, what was the standardized version, so after it was standardized, and then we're using the standardization formula in reverse. So the third part, in 2016, 150 of the 15-year-olds in that country were randomly selected. Now, at this point in the question, you should be going, ding, 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 we are talking about a sample. A sample. As soon as we're talking about a sample, we're going to be talking hypothesis testing. Okay, so their weights are recorded. If it was found that their weights are normally distributed with a mean weight of 62 kg, and standard deviation of 10 kg. Now, the mean weight of 62 kg is the mean of the sample, okay, not the population, the mean of the sample. So the mean of the sample is represented by x bar. So x bar is 62. The standard deviation is 10. We had mu in the previous part, so mu was 63.5, don't forget that. And the sample then contains 150 people, so n is 150. So they are our pieces that we need to pull out of this. So it says test the hypothesis at a 5% level of significance, okay, or we would say a 95% confidence level, same thing. The mean weight of 15-year-olds in that country had not changed from 2015 to 2016. So basically our hypothesis testing starts with H0. H0 is what's called our null hypothesis. Think nothing has happened. So the null hypothesis basically is mu is equal to what it always was. So in words, what we would say is that the mean weights of 15-year-olds in that country have not changed from 2015 to 2016. H1 then is our alternative hypothesis, and we're only ever going to have our null and one alternative. So that's mu does not equal 63.5. So we're not saying greater than, less than, we're just saying it's not equal to. So what that is saying is that the mean weight of 15-year-olds in that country has changed from 2015 to 2016. So it's absolutely fine to write your null hypothesis as mu, and mu equals and mu does not equal, but make sure for yourself that you understand what it is, and what it means, and what it represents. So there's a few different ways of doing this. You can work out, first of all, a confidence interval and use your confidence interval, and that's absolutely fine to do. I'm actually going to use my standardization formula. So I have the one specially for a sample, which is very similar to the one we used in the previous two parts. The only difference is instead of x, we now have x bar, and instead of just sigma on the bottom line, we have sigma over root n. So working with that, it's 62 minus 63.5 all over 10 square root of 150. So when you work that out, we get minus 1.8371. So we want to see, well, for a 5% level of significance, so 5% level of significance, we're talking about Z being between minus 1.96 and positive 1.96. So since minus 1.8371 sits in there, we would accept the null hypothesis. So what we would say is, since minus 1.96 less than or equal to minus 1.8371, 8371 is less than or equal to 1.96. We accept the null hypothesis. Sorry, now it's getting to the bottom of the page. So we accept the null hypothesis. So basically we're saying mu is equal to 63.5, and then that's fine, but we still need, from here, we still need to come up and give our conclusion. Okay, so what can we conclude? So back to what they asked us, mean weights of 15-year-olds, and I'm taking this straight from the question, in that country have not changed from 2015 to 2016. So that's really important. So they've asked you to state your null hypothesis, state your alternative hypothesis, give your conclusion in the context of the question. Like, they couldn't be more clear about this. Simply saying I accept or reject the null hypothesis is not enough. Have to bring it back to the question. If you decided to work with creating a confidence interval, same idea. Working with the confidence interval, you would create your confidence interval, and you would find that your mean sits in there. The mean of 62, the x bar, the mean of the sample, sits within that sits within that confidence interval. So it's absolutely fine. Both methods absolutely valid, and we've seen questions before where they've kind of led to a specific method, but in this case it was quite an open question. We hadn't done a lot up to this point, so both methods, much of a muchness. I just generally would prefer to work with this formula rather than creating the confidence interval for the mean.